Hello, Chem 212 students, and welcome to this week's lectures on alcohols and phenols. Uh, in this chapter, we're going to learn about a lot of reactions, or we're going to really review a lot of reactions that we've learned in the past. In chapters 7 and 8, we learned how to do substitutions to produce alcohols. We also learned how to produce alcohols by addition reactions in chapter 9. And so we're going to see some of those reactions again today. We're also going to see some new reactions that involve alcohols. So let's get started. Here you see a picture. This picture is of ethanol 85 gasoline, which stands for 85% ethanol in the gasoline, which certain cars can run. It was a little popular for a little while, less popular now. They can actually make the ethanol by fermenting the sugars from corn. So that was part of the reason why it was popular. Although it turns out you're still burning things, you're still putting carbon in the atmosphere, so it's not perfect, but yeah. We also have isopropyl alcohol here, which is, we have a bottle of there. You've probably seen that before. Um, so alcohols, they are said to possess this hydroxyl group. You've probably heard me use this word before, but now it's officially defined now that we're in the alcohol chapter. The oxygen bonded to hydrogen is called the hydroxyl group as long as there's nothing else. That's one particular functional group, the alcohol hydroxyl functional group. So you can see it here in ethanol and in cyclopentanol. Hydroxyl groups, you're going to see them all the time in natural molecules. Here's a couple of examples. A sex pheromone in a insect here, and also an antibiotic medication. But I mean, you can look at many examples of OH groups, hydroxyl groups in natural compounds. They're all over the place. Here's a couple more in cholesterol. So here's cholesterol. You can see that we have OH group right there. And also we have the OH group right here in vitamin D3, the hydroxyl group. Also here, geraniol, which is used in perfumes. It's a kind of rose floral smell. But really, you're going to see these in all kinds of natural compounds. Also common in natural compounds are phenols. So phenol are considered a different functional group and have a different name than just regular alcohols. And a phenol is what you call it when you have an OH group that's directly bonded to a carbon that's on an aromatic ring, a benzene ring here. And again, these are super common in natural compounds. For example, dopamine here has a phenol. This one called urushiol. You'll find it in poison ivy, and it causes irritation to the skin. Capsaicin, which is the compound of spiciness, and THC, which is the primary psychoactive ingredient in marijuana or cannabis. And so phenols are present in lots and lots of organic compounds as well, or biological compounds. So we're going to start off, like we have in many chapters, by talking about the nomenclature of these guys. So alcohols are named using the same procedure that we used in previous chapters. The big difference is now our most important group is the hydroxyl OH group. And so our primary chain, our parent chain, must include the OH. And we're going to talk about priorities now, because we've had a few groups where we said, oh, this is the higher priority, this is the higher priority, right? So now we're going to have to start to identify these individual priorities, and we'll continue to expand upon this priority list as we move on to talk about other functional groups. And so we want to have the parent chain include this OH group. And so as usual, we're going to identify other substituents and name them. We're going to assign locants, and again, that locant here is going to, in this case, be assigned such that the lowest locant will be assigned to the carbon attached to the hydroxyl group, given that it is the highest priority. Then we're going to list the substituents in alphabetical order, ignoring prefixes except iso. And then finally, we're going to place the locant for the OH group immediately before the end of the parent name or before the ol suffix. So similar to alkanes and alkynes, what we're going to see is that the OH group is going to be even higher priority than those. So here, if we have this 5-carbon chain, we know that's called pentane. And the difference here is that when we have an OH group now with 5 carbons, so 1, 2, 3, 4, 5 carbons, so we say pentan, but then we end with all because there's an OH group attached here. And like what we saw with the alkenes and the alkynes, the parent chain must include the OH even if that's a shorter chain. So in this case here, we have a 4-methyl octane. So the parent chain here is octane with 8 carbon atoms. However, here we can see that this has 8 carbon atoms too, going from left to right. 1, 2, 3, 4, 5, 6, 7, 8. But the parent chain is not going to be octane here. Instead, it's going to be the one that has 6 carbons. 1, 2, 3, 4, 5, 6. Because that chain can contain the hydroxyl group. And when we give locants, we're going to give this one locant number 1, closest to the hydroxyl group here. And so the parent chain here is going to be hex for 6 carbons, and because there's no double bonds, and all because this contains a hydroxyl group, the alcohol group here. So now we're going to introduce the idea of priorities here, because we will have lots of compounds that contain multiple functional groups, and we're going to have to end up eventually naming these too. So here we can see an example of a compound that contains both the alcohol functional group and the alkene functional group. And so for now, we've got 3 new functional groups with priorities that we've built up to. And alcohol is going to be the highest priority functional group. What that means is that if there is a hydroxyl group on your molecule here, you're going to assign the parent chain such that it contains that functional group. Also, the locants will be assigned such that the lowest locant goes to that highest priority functional group. So in this case, where we have an alcohol functional group and an alkene, our locants are going to be assigned as we see on the left, 1, 2, 3, 4, 5, 6, 7. Now notice 7 here, this includes the alkene group as well, being the second highest priority group. But our locant starts from the left side to give the hydroxyl group the lowest locant number. We would not start from the other end, 1, 2, 3, 4, 5, 6, 7. This would be incorrect. We will not do it this way. The reason being because that would not give the OH group, the hydroxyl group, the lowest locant priority here. So in terms of priorities, so far we've got 3 types of functional groups that have priorities. Methyls and so forth, these do not have a priority to them. Alcohol is going to be the highest priority functional group, followed by alkene, finally alkyne being the 3rd highest priority. And so we're now going to assign the parent chain based on the highest priority functional group, and also the locants based on the highest priority functional group. And we're going to end the parent chain name, of course, with a suffix that corresponds to that functional group. So here, this name would end with a heptanol. But we'd also have an ene, so that's something to think about here. Okay, so let's move on and just focus on alcohol for now. All right, so when it comes to the alcohol here, we also have to state a locant that says where on the chain is the alcohol functional group. So here we have a parent chain that contains 5 carbons, 1, 2, 3, 4, 5. So it's going to have the prefix pent, indicating 5 carbons. It's going to end with anol because it has the alcohol group in it. And that alcohol group is on the 3rd carbon. So we would say either 3-pentanol, or we can say pentan 3-ol. And sometimes when we have an alkene and an alcohol group, we're going to have to put the 3 here, because we're going to put another locant to indicate where the alkene is, and we'll want to put that in front. And so that's something to keep in mind there. So here we have, for example, here is cyclopentanol, so it's cyclopentane, but then we end with all because it has an alcohol group. Okay, we could say 1 cyclopentanol, but we don't have to, because It's kind of a given that if there's only one group, that's the alcohol, it's going to be on the first carbon. We would always number such that this is number 1, right? Then it wouldn't matter what we call number 2. We just go around the chain. Now that is different if we have other functional groups present. So notice here, this carbon is also not chiral because going around the ring both ways, it's the same either way. However, if we have other substituents, like in the example on the right here, that is not all the same all the way around. So this direction is different from this direction. So in this case, this carbon is now chiral. Okay, so let's analyze how we would name this. Number 1, we have a hydroxyl group, which is the high priority group. So our name is going to end with -al. Also, I'm just going to say something about the "an." The "an" says that there's no "enes" basically, or "ines." So if we're going to get running to examples where we have ene-als, alkenes that also have alcohols, and then we would say something ene-al. But since this is all single bonds, carbon-carbon single bonds, we're going to say an-al. Okay. Now the prefix here is going to be cyclopent. Cyclopent is because this alcohol, this hydroxyl group, is attached to a cyclopentane. Cyclo because it's in a ring, and pent because it has 5 carbons, and ane because it's all single bonds. Next, we have 2 methyl groups. So we're going to say dimethyl, a methyl here and a methyl here. So that covers our dimethyl. Now, in terms of locants, the highest priority group is the alcohol, so it gets locant number 1 here. Then we could number around as going the other way, 2, 3, like this, 2, 3, 4, but we would not do that because that would give our substituents, the methyls, a higher locant. We want the lowest possible locant. So just like before, we're going to number around the ring such that it gives us the lowest locants so we get to the next group as quickly as possible, right? So we get here 2, 3 on the third carbon, we get to our methyls. So we're going to see 3, 3 for the 2 methyl groups, both on carbon number 3. And then finally, we would have to assign R or S. In this case, it's R, and just by way of review, we can talk about this real quick. Our OH group here is going to be assigned the highest priority due to the oxygen being the highest atomic number group. We'll also have a wedge here, which is the hydrogen, and then we have 2 lines here. So the hydrogen is going to be assigned the priority number 4 because it is the lowest atomic mass. And then in terms of these 2 carbons, these are going to be tied. They're going to be a carbon each attached to 1 carbon and 2 hydrogens. This one too is attached to 1 carbon and 2 hydrogens. So we have to go to a tiebreaker. This carbon is attached to 3 carbons. So it's a carbon, carbon, carbon. And this one is attached to 1 carbon and 2 hydrogens moving forward. So in this case, this second carbon beats this hydrogen. So we would call this direction number 2 and this one number 3. At that point, we need to do a double switch so that we get the number 4 on the dash. And so we can switch it like this, the double switch. And that will preserve the stereochemistry. And so now we can redraw this. So we're going to go now to the dash now and the wedge and the line and the line. And now that we've switched, our dash is going to be 4, which is what we want to assign R and S. This wedge will be 1, this line will be 3, and this line will be 2. And now we will assign the R and the S. The 1, 2, 3 goes 1, 2, 3, right hand turn. And so that's why we have an R here. And so that's the nomenclature here, including the stereochemistry and other groups here. There are also some very common names that you're going to hear. For example, if we're looking at this naming the IUPAC name, the parent chain is going to be prop since there's 3 carbons, and since it's alcohol, it's going to end with anal, so propanol, and that alcohol is going to be on the 1, 2, 3 on the second carbon. So we would call this 2-propanol by the systematic name, and that's the way I would prefer for you to name it. But everyone calls this isopropyl alcohol because this group here as a whole, if you recall, hopefully you remember this group is called isopropyl group, right? Isopropyl as a branch. And so isopropyl alcohol is a very common way to name it. Similarly, this group is called a tert-butyl group. And that's something we learned, way back in chapter 2. So this is often called tert-butyl alcohol, although if we were naming it by the IUPAC name, again, the parent chain would have 3 carbons, and so we'd call it propanol. And on the second carbon, it has a methyl and an alcohol, so we'd call it 2-methyl-2-propanol. Finally, here we have phenylmethanol. So here, the parent chain only contains 1 carbon. That's what we call it, methanol. Then it has this group here, which is called a phenyl group. So notice here that the parent chain is the 1 carbon. Why? Because that contains the alcohol, and that's the highest priority. So that's why we call the parent chain methanol, because the parent chain is that 1 carbon that has the alcohol. It has the highest priority. And then, so that makes this whole phenyl a branch, basically. So when we have a benzene ring as a branch, we call it a phenyl. You've seen that before as well. But often this is called benzyl alcohol because it's in the benzyl position, 1 carbon away from the alcohol. So these common names are super common. You're going to probably see them on bottles in the lab, unfortunately. But again, it's just some of those common names stick. But we prefer the IUPAC name because it's 1-to-1 with the structure. If you know the name, you know the structure, as long as you know the system. And if you know the structure, you know the name, as long as you understand the system of naming. Okay. Now, like with halides, we talk about the positions of the carbons relative to the main group we're looking at. And we also talk about the number of carbon atoms attached to the carbon that's attached to our functional group of interest. So here, our functional group of interest is the OH, and it's the alpha carbon is the carbon attached to that OH. And we name the alcohol as primary, secondary, or tertiary based on how many carbons are attached to that alpha carbon. So if there's 1 carbon attached to the carbon that's attached to the hydroxyl group, we say that's a primary alcohol. If there are 2 carbons, we say it's a secondary alcohol, and if there are 3, we say it's a tertiary alcohol. And that's going to influence the way some reactions happen, and so that's why that terminology is important. When the OH group is attached directly to the benzene ring, we call it a phenol, and that is its own parent name, phenol. So that's a little bit different about that. So when you look at the alcohol attached directly to the benzene ring, that gets its own special name, and it's called phenol. And so any compound where that is the main functional group, the alcohol on the benzene ring, the parent name of that compound is going to be phenol, and that's part of the IUPAC systematic naming. The reason why it gets its own name is because phenols behave chemically very different than other alcohols. You may remember that they're significantly more acidic because if you remove the proton, your anion has significant resonance stabilization. And so that leads to very, very different chemistry. And so we give it its own name because it has its own special chemistry. So here we have a nitro group, we have a chloro group. So we're going to number around the chain so that we get the lowest number. So this would be carbon number 1 because it has the alcohol, the highest priority group. Then we'd number this way to get to the next group, which is nitro. So we say 2-nitro, then 3 and 4, and so we say 4-chloro. Fluorochloral 2-nitro phenol. But the main idea is that when you have an OH group on the benzene ring, you have a new special parent name. That parent name is phenol. So alcohols, super important to all kinds of industry. As I said, hydroxyl groups, we're going to find them everywhere, very, very common. Methanol is the simplest alcohol. It's an alcohol with one carbon. Um, Lots and lots of methanol are made industrially from CO2 and H2. It does require energy to be put in. It's an endothermic process, and with a catalyst, it's possible. Methanol is very useful as a solvent. We've used it as a solvent in our labs. It can be used to make other substances, as we've seen. For example, if you do an elimination, right, on the or dehydration elimination, you can make ethene. It's used as fuel as well. You can burn it. So very, very common. Even more common and useful is ethanol or drinking alcohol. The advantage of ethanol, what's great about it is it can be produced biologically. We did that in lab this semester. It can be produced by fermentation. Um, and Industrially, there's lots and lots of acid catalyzed hydration of ethene or ethylene, as the common name goes. So we dig up, we get these fossil fuels. Ethene is a gas. We react it with water and do an addition reaction, and we can make ethanol. So ethanol is a great polar product solvent as well. It's useful as fuel. We burn it all the time for various reasons. Uh, if if it's sold as a jug of ethanol for like perfume usage or something like that, it's often denatured, which means they'll add methanol and maybe some other minor component to make it smell and taste bad so people won't drink it. Otherwise, it has to be taxed like drinking alcohol, which has a lot of taxes to it. So ethanol can be drank if it's not denatured, and it's often taxed. Just the sin tax, as they call it, just to cover medical costs and things like that associated with alcohol consumption. Isopropyl alcohol, isopropanol, or rubbing alcohol is very commonly used as a solvent to clean things off. Um, it's got this kind of middle-ish polarity to it. It's quite polar because of the OH bond, but still it has three carbons, so it makes it a little less polar than some other things. So it's a good kind of all-purpose solvent. It's also an antiseptic, and it's also added to gasoline as well. Like all of our gasolines usually have at least 10 to 15% of alcohols of some kind, mostly ethanol. Um, the alcohol group is huge for physical properties. The reason why it's big is because it has an OH bond. Let's think back. What does that mean? That means it does hydrogen bonding, right? Has a very polar bond there. So if you have two alcohols right next to each other, the oxygen is pulling electrons away from the hydrogen, very, very electronegative. So that makes it partially negative on an oxygen on one of the alcohol molecules. But likewise, the hydrogen is partially positive. So if you have two of these alcohols molecules close by, you get hydrogen bonding. Of course, this is very important in water. It's a very strong intermolecular force. So what that means is that the molecules stick together very quite strongly, and that leads to higher boiling points. You have to get them jiggling faster to get them to evaporate and separate and fly all around separately instead of sticking to one another and staying as a liquid. So you can see that if we just have ethane with no functional group, no polarity at all, its boiling point is super low, negative 89 degrees Celsius. We get a little bit of polarity here. This bond is polar. Um, so here we have only London dispersion forces, right? So relatively weak for a small molecule like this. Here, we got a polar bond, so we have a little bit of dipole-dipole forces, and so that leads to a little bit of attraction, which raises the boiling point a little bit. Here we have very strong dipole-dipole interactions called hydrogen bonding, and so these intermolecular forces are super strong, relatively speaking. Of course, all intermolecular forces are weak compared to chemical bonds, covalent bonds, ionic bonds, so forth. But um, that means a pretty strong attraction between ethanol molecules. And, for water, even if you go to water, water has kind of a double hydrogen bond. So, water, the boiling point is 100 degrees Celsius. So, it's even stronger. There's kind of like a double hydrogen bond going on. And so when you have these OH groups, these lead to strong hydrogen bonding forces, which means higher boiling points. In terms of solubility, alcohols are interesting because they generally have the alcohol part, That's very polar. Then they have the carbon part, which is not polar, right? All these carbon hydrogen bonds are not polar. So the fewer carbons you have, the more important is the OH part, which is polar. And so since this is polar, it's more attracted to water, which is also polar. So we call that the hydrophilic region. Hydro meaning water, philic meaning loving, water loving. So this is attracted to water. We call the hydrocarbon part, which is not polar, we call that the hydrophobic region. Now, if you have very few carbons, 3 or less, uh, these alcohols are completely miscible with water in any proportion. You can mix them in any proportion because the hydrophilic region dominates. However, for longer chain alcohols, for example, we have octanol here. Um, the hydrophobic region dominates. And so this molecule here with 8 carbons is more nonpolar than it is polar. And so they don't mix very well with water at all. If you have 4, 5, 6 carbons, then they mix okay with water. They're kind of in between polar. They're kind of polar. But 3 or less, they mix completely well with water. If you have more than 6, they don't really mix at all with water. They become quite nonpolar overall. And so this is why, if you look in some of your cosmetics and stuff, you're going to see that there will be some of these, like you might see decanol or octanol, because these are nice emulsifiers. They have a polar part. They're not really great because they don't have a huge polar part. They have a small polar part and a large nonpolar part, so they help to make the non-polar components, the oils in your cosmetics, your shampoos and stuff, mix with the water components, the aqueous components in your cosmetics, and so they're a common cosmetic ingredient. Um, in terms of antibacterial agents, so the antibacterial properties of the alcohol really depends on how big the hydrophobic group is. So the alcohol is going to need some water solubility so that it can get to, because we're mostly water, or whatever we're interacting with often has water. And so it needs to be able to travel through an aqueous medium to get to the bacterium. But the antibacterial action of the alcohol is the hydrophobic region, which cell membranes are mostly hydrophobic. They're mostly lipids except for the outside. And so when that larger hydrophobic region gets into the cell membranes, it interrupts them, and then it can open up the cell of the bacterium and causing it to die. And so you'll see that in terms of the alkyl chain length, 7 or 8 carbons is the maximum antibacterial effectiveness of alcohols. Here's an example of an antibacterial phenol. So phenols are very commonly used as antibacterial agents. This is hexyl resorcinol, used as an antibacterial and antifungal agent. There are other modified resorcinols here that are also used for like mouthwash and stuff like that. So this has a good combination of hydrophilic parts here, 2 hydroxyl groups, and hydrophobic parts here. And so that kind of balance allows it to be effective as an antibacterial agent. In terms of acidity, so again, I already pointed out kind of the difference in the acidity of alcohols versus phenols, right? Phenols being more acidic. The way we can evaluate the relative acidity of alcohols is the same way we did in the acid-base chapter 3. We considered REO, right? REO, atom, resonance, induction, orbital. And the key component here is going to be atom. The atom is oxygen. It's electronegative, but it's not too large. So it doesn't stabilize a negative charge as well as a sulfur atom, for example. But it is electronegative enough to stabilize that negative charge somewhat. So alcohols are not great acids. They're kind of middling acids, right? So what you need is a pretty strong base to deprotonate an alcohol. It's not a great acid, just like water isn't. Water's not a great acid. They're okay. And so you need a strong base, an amide, a hydride ion to deprotonate an alcohol. So we could use sodium hydride. So that would do a proton transfer here. The H minus ion would grab that proton. You'll get hydrogen gas, and that hydrogen gas will leave, which by Le Chatelier's principle will drive this reaction to the right. And that would leave a alkoxide ion. So that's what we call this when we have the negative charge on the oxygen and we have an alkane chain attached to that oxygen. We call it an alkoxide ion. We can also use metals to deprotonate this, and we get an ionic compound. So sodium, potassium, lithium, they really want to give away their electron and become a positive ion. And so when they do, you'll get two hydrogen atoms which will come together to make hydrogen gas. And then at that point, they leave an electron on. So it's almost like a radical reaction, really. So you've got this one electron. So you got one electron here, right? But you're not really making a bond. It's just giving away that electron here. And then this hydrogen takes one electron with it. It's not really an ionic reaction. I probably shouldn't say this. But in the end, one electron gets left on the oxygen. That's what's important. And so now you've got this, right? You got this, or in fact, both of these are left. Anyway, the point is that this sodium loses this electron, right? And the hydrogen gas, you'll get basically two hydrogen atoms, hydrogen atom, and these together, each with one electron, they can now make H2. And then you have this alkoxide ion left. And so these are ways you can get an alkoxide ion by reacting with a strong base or a metal. In terms of the stability of alkoxide ions, they're not particularly stable. Remember, our halides, these are great at stabilizing a negative charge, right? Remember, there's two factors to being able to stabilize a negative charge. Number one is the electronegativity of the atom. Number two is the size of the atom. So a larger atom that is electronegative is going to be the best for stabilizing the negative charge. So we're talking like iodide here out of all the all of the halides would be the best. It's the largest and it has a pretty strong electronegativity. Oxygen, it's pretty electronegative, but it's pretty small, so it doesn't stabilize the negative charge as well as like a chloride or something because it's so small. Remember the very strong small refrigerator magnet versus the big terrible pizza magnet, right? The small strong magnet sticks your paper to the fridge better. That means it's more reactive with your fridge. This is more reactive with other things. If it finds a positive thing, it will be more likely to want to react with it. The amides are even less stable. These going to get a proton anywhere they can get it. And the least stable were the alkylides and alkyl ions. These ones that is just a carbanion, basically. Remember, we can use REO to rationalize the relative acidity. Basically, we look at, since this is the most stabilized negative ion, a hydrohalide, which would produce that ion when it loses the hydrogen atom, would then be the strongest acid. It would produce the most stable anion. And then the less stable anion here would be the alkoxide, so less acidic here. Less stable anion, the amide ion here would be even less acidic. Its conjugate acid would be even less acidic. And then the conjugate base for this carbanion, these would be even less acidic because they produce an even less stable conjugate base. So also a part of REO was resonance, right? After atom was resonance. So if we look at, for example, cyclohexanol, it has a pK of 18, but phenol has a pK of 10. So phenol is literally 100 million times more acidic than an alcohol like cyclohexanol. And that is because if you deprotonate the phenol, you get a carbanion here on the oxygen, and there's significant resonance. There's 5 different resonance structures here. And so that really increases the acidity of the phenol, because the conjugate base can really stabilize the negative charge due to resonance. And so that's something to keep in mind. That's why phenol gets its own name. That's why it's its own compound. We consider it separate from just regular alcohols, because it is 100 million times more acidic than just a regular old alcohol. So it's kind of its own different thing chemically. Induction is also important in terms of ARIO, so we're going down the list. Atom, resonance, induction. So if you have a highly electronegative atom attached to the beta carbon, so this would be the alpha carbon, this would be the beta carbon. You have a highly electronegative atom, such as fluorine, chlorine, attached to the beta carbon on the alcohol. That's going to increase the inductive effect, stabilizing the negative charge of the conjugate base here, and so you get a much stronger acid. So we can see that here in terms of pKa. So trichloroethanol has a pK of 12.2, almost 4 lower than 16, the pKa of ethanol. So that this inductive effect here is making this trichloroethanol almost 1,000 times, 10 to the fourth, 1,000 times more acidic than just plain ethanol. Also, the solvent will matter a lot. And sometimes, if you think of just a bottle of ethanol or something too, its solvent is itself, right? And so, in terms of solvation effects, the the more poorly solvated the conjugate base, the less stable it is, the less acidic it is. So, when it comes to tert-butanol, all these big bulky methyl groups here make it difficult for it to solvate itself, or for some other polar solvent to solvate it. And so the tert-butanol is less acidic in these solvents than ethanol would be. There's a picture here of that, and we've seen this same picture before when we were talking about solvent effects before. With tert-butoxide, with the conjugate base of tert-butanol, you've got all of these non-polar groups here hanging off. The solvent, if it's polar, will only really be attracted to where the oxide ion is here. Whereas with ethoxide, it's a lot more open here, and so you've got all this open space for the solvent, which is polar, to also be attracted to that negative ethoxide ion. So due to that steric hindrance, the tert-butoxide is not well solvated, and so the tert-butanol is not quite as acidic as ethanol. And in terms of making alcohols, we've already talked about the reactions involved in making alcohols. We talked about them back in chapter 7. They were substitution reactions. And we would start with an alkyl halide, and we react with an alcohol, with a nucleophile, which is generally can be for example, hydroxide here. So, and these can occur by either SN1 or SN2. In this case, is a primary substrate, so this would likely occur by SN2, right? Because it's less sterically hindered. So if we had the hydroxide group here, we would have a nucleophilic attack on the alpha carbon on the alkyl halide, and a simultaneous leaving of the chloride. And so then we get the primary alcohol. And of course, we'd still have the sodium ions, we'd still have the chloride ions, and we can just write that as sodium chloride. Now, if it's tertiary, then, well, one other thing too is you may recall that there's going to be E2 competition here, right? Competition, E2 competes. So you're going to have also a minor E2 product. That's something to keep in mind, right? You'd also end up, because OH minus is a strong nucleophile, but also a strong base. So you'd also get some of this too. So it's not the ideal situation, right? You'd also get a little bit of the E2, but you get primarily the SN2. Here, you'd get a mixture of SN1 and E1 if you had a strong nucleophile, strong base. However, we have actually we have a weak nucleophile and weak base in this case. So we would still get it's tertiary with a weak nucleophile, weak base, so we'd get a little bit of elimination as well, but this would proceed through a SN1 mechanism, meaning the The leaving group would leave first. We'd have a carbocation intermediate, which would be okay in this case because it's tertiary, so it's somewhat stable. And then at that point, we would, after that, we would then have the attack by the water, which is the nucleophile here. Oops. Okay. We'd have the attack by the water. So I'm going to have the water attack here. It's got its, I want to make these blue. So this would attack right in there. And then, of course, we would get the protonated. We'd still have, since we're attacking with a neutral nucleophile, we'd have still the oxygen with 2 hydrogens attached. And it'll have 1 lone pair, so it'd have a positive formal charge. We'd have to have a water come in here and deprotonate that guy, right? So the water would come in here and it would finally deprotonate it. And then finally we'd get our product. But it's important to keep in mind that also we would get E1 as well, right? So we'd get a little bit of the elimination product as well. And that elimination product would be the E1 product here. Would be like this. It would be the more substituted product, right? Like that. So we'd get some of that too. But we can make alcohols by substitution reactions, by reacting with hydroxide as a strong nucleophile, strong base, or weak nucleophile, weak base with a tertiary substrate. So if you forgot this from chapter 7, it's time to go back and review before the final. This is still relevant. We can also make alcohols via addition reactions. So we talked about this in chapter 9. We can do an acid catalyzed addition, which will give us the Markovnikov addition, where the alcohol will go on the more substituted carbon, in this case on the second carbon here. We could also do an oxymercuration demercuration, which would also give us a Markovnikov product with the alcohol on the more substituted carbon. Remember, the advantage of this is when we do this, then this is no carbocation rearrangement. So if we're trying to avoid a carbocation rearrangement, this would be important. In this case, we don't have to worry about it because there's no more substituted carbon close by. If we want to do an anti-Markovnikov addition, where we have the OH on the less substituted functional group, we use a hydroboration oxidation. And so the OH here would go on this one. So these are reactions we've already seen before. Nothing new here. These are just how we make alcohols. We already know how to make alcohols from previous chapters. Now, these aren't the only way to make alcohols. There are other ways. We can reduce a carbonyl. So what's a carbonyl? I've used that word somewhat before, but carbonyl means a carbon double bond oxygen. That's a carbonyl. A big chunk of Chem 213 is going to be studying the reactions of various types of functional groups that have carbonyls as a part of them. Aldehydes, ketones, carboxylic acids, amides, so forth. So there will be an oxidation or reduction. Remember in Chem 151, the way that we thought about oxidation reduction was we looked at we determined the oxidation number and see, did it go up? Then we call it oxidation. Did it go down? We call that reduction. A little bit easier way that I like to use in OChem is that if we oxidation is if we add oxygen atoms. Atoms are bonds. So, for example, if we make a double bond to oxygen instead of a single bond, that's oxidation. And it will be reduction, if we it will be also oxidation if we lose hydrogen atoms. And then the opposite will be true. If we lose oxygen atoms, that will be reduction. If we gain hydrogen atoms, that will be reduction. Okay. So if we add oxygen or lose hydrogen, that's oxidation. If we remove oxygen or gain hydrogen, that's reduction. And that's kind of the easier way of looking at it in terms of OChem. And that's usually all you need to do anyway. although we can assign oxidation states. So I'll just remind you how we do it. To determine the oxidation state of of an atom, what we do is we imagine that we've divided every bond exactly in half. So we divide the bonds exactly in half here, and then we look at so that's formal charge here. Sorry, let me restate that. So it's kind of like formal charge, except we do it differently. So we've done formal charge before, and what we do is, remember, we split every bond in half, and we gave each atom its dots, right? We said, oh, carbon has 4 dots. That means it has no formal charge because it's supposed to have four valence electrons, since it's in group 4, and it has 4 dots, so no formal charge, right? There's no formal charge at all on this. What we do different is that when we assign oxidation states, we give the more electronegative atom all the electrons in the bond. So for example, the oxygen is more electronegative than the carbon, so we give it both of the electrons in the bond. Okay. And then the hydrogen here is less electronegative than the carbon, so we give the carbon both electrons in its bond, and we do that 3 times. And then we compare. Oh, okay. And for the oxidation state here, for the carbon, it's got 3 negatives and 1 positive. So we say that it has a oxidation state of -2, right? It has these 2 extra electrons, basically. So that was this example here. It's -2. The carbon is oxidation state -2. Now, in this case with carbon, we do the same thing. We give all the electrons in these bonds to carbon because carbon's more electronegative. That gives it 8 electrons. Okay, so 8 electrons minus the 4. So 4 is what it's supposed to have, but it has 8. So it has a net of -4. So its oxidation state of the carbon here is -4. Now, let's say we change this hydrogen to an OH bond, right? We've essentially added a bond to oxygen. Do you see how the oxidation number went up? Adding bonds to oxygen is oxidation. So that's the easy way to look at it. I see this as oxidation. More oxygen atoms. Oxidation. So I didn't even have to to calculate oxidation numbers to know that. That's why I think that's the easier way. But you can calculate oxidation numbers. We just did it, right? In this case, the carbon had 6. So it doesn't get these electrons. It got these 2. So just going back to that last slide, it gets 6, right? 2, 2, and 2. So it should normally have 4 because it's in group 4, but it has 6, so it has an oxidation state of -2. But as you saw, I could tell that if I turn methane to methanol, that's oxidation, without even knowing these numbers, because the carbon has 1 more bond to oxygen. That's the easy way to do it, and that's the way I usually do it. Now, I also said if there's more bonds to oxygen, that's also oxidation, right? So now this carbon has 1 bond to oxygen, but in formaldehyde it has 2. So going this way is also oxidation, more bonds to oxygen. But we could calculate the formal charge of the carbon just the same way we did before. We give the oxygen all the electrons in this bond. So let's break it down here. So this oxygen is going to get all the electrons here. So it gets the 2. It gets all of them in the bond. It started with 2 lone pairs, right? Now it has 8. So the carbon doesn't get any of those electrons. But it gets both of the electrons from the hydrogens. And the hydrogens get none. So now it has 4, or it starts with 4. It's from group 4 valence electrons, and it has 4. So it has 0 oxidation number. But I didn't need to calculate the oxidation number to know that going from methanol to formaldehyde is oxidation. I just saw that the carbon went from making 1 bond to oxygen to making 2. More oxygens and more bonds to oxygen is oxidation. So that's the easy way. No need to calculate these numbers, but you can, right? Likewise, we could do the same. We could do similar things here. So now this carbon here, at this point, it's only going to have 2 electrons. So it would be basically 4 minus 2, which is positive 2. And then here, the carbon doesn't get any of the electrons. All the electrons all go to oxygen. So 4 minus 0 equals 0, equals positive 4, rather. And so you can calculate the oxidation numbers. But I just see more bonds to oxygen, more oxygens. That's oxidation. Makes it easy. And that's kind of the shortcut that I suggest you use too when you're studying organic and especially biological chemistry. It just makes it so much easier. Likewise, if you have fewer bonds to oxygen, or you've added more hydrogens. That was the other way I said, right? Let's talk about adding hydrogens now. This is the other way you can see it. It's the easier way in organic chemistry, like I said. So here, we already determined that this was oxidation number 0, and this was negative 2. So that's reduction, right? But the easier way to think of it is there's fewer bonds to oxygen. This is 2 bonds to oxygen. This is 1 bond to oxygen. Reduction. Fewer bonds to oxygen. Or you can think adding more hydrogens on. Sometimes that's easier. There's no hydrogens on this carbon. There's no hydrogens on this oxygen. But now we've added 1 hydrogen to this carbon, and we've added 1 hydrogen to this oxygen. We added H atoms. Reduction. Okay. Fewer bonds to oxygen. More bonds to hydrogen. Reduction. So that's kind of like my easy, simple way, a suggestion for you to think about oxidation and reduction in organic chemistry. If you have to deal with metals, you're going to have to go and calculate oxidation numbers, okay? But if you're just doing, carbon, oxygen, hydrogen, this is the easy way to go. So how do we do it? Same way we hydrogenate any pi bonds, same way we did for alkenes. H2 with a catalyst, platinum, palladium, nickel, some metal, and we'll get hydrogenation. So we end up adding a hydrogen here and a hydrogen here, right? That's adding H2. And so it's the same as we saw with the alkenes. We just add hydrogen atoms on. So how do we do this? We can use hydrogen, but the problem with this is that it's not practical. To do this, a high temperature is required, and you want a high pressure of hydrogen gas. This is energetically expensive. There are cheaper ways to do it. And so what we do is we get something that really, really wants to give away hydrogen atoms. For example, sodium borohydride. And then we can use a polar protic solvent of any kind, ethanol, methanol, water. This will reduce for us too. So this is a strong reducing agent, sodium borohydride. Let's think about why is it a strong reducing agent? Well, first of all, let's look at the mechanism first. So if we look at boron, boron is in group 3, right? And if we do our formal charge thing with the dots, we see that it has 4 dots, like if we draw a circle around it, right? So its formal charge is -1. That's why we have the -1 charge here. It would have a formal charge of 0 if it loses 1 hydrogen. That's why it wants to lose the hydrogen. And so the mechanism here is that the bond between and it's a little bit different than some mechanisms you've seen, but basically we're just saying this bond between boron and hydrogen is becoming a bond between hydrogen and oxygen. And then we have this kind of resonance arrow that puts the electrons up here on the oxygen so that carbon is not making 5 bonds. Okay, and then at that point, this is why we need the protic solvent, because the protic solvent is going to provide the proton. And so at that point, this alkoxide ion needs to be protonated, so we get a proton transfer, and then we get the alcohol. And so notice that borohydride, it doesn't really want this, right? Because what you get at the end, it's not written, but you have now borane, and now this borane has 0 formal charge. The boron has 3 dots, and boron is in group 3, so it wants 3 dots in terms of formal charges, right? So it's 3 minus 3 is 0, 0 formal charge. So this borohydride wants to get rid of that proton. That's why, or wants to get rid of that hydrogen. That's why it's a good reducing agent. It's not a proton. It's getting rid of a hydrogen, hydride ion essentially, because it's not a proton. Notice this is not a proton transfer. We call it a nucleophilic attack. Why is it not a proton? because a proton would be leaving the electrons behind. It's not a proton, it's a hydride ion. It's actually taking both of the electrons with it to make a bond to that carbon. So when it comes to making this, reducing this carbonyl, remember this carbonyl is flat. So this carbon has 3 bonded atoms and no lone pairs. This is trigonal planar. So just like a carbocation, this reduction can happen from either side. So you're going to get a racemic mixture of products if you're ending up with a chiral center. So that's something to keep in mind. This thing is flat. So it can the attack from the nucleophile, which is a hydride ion, can occur from either side in equal probability. Now, an alternative to sodium borohydride is lithium aluminum hydride, or LAH as it's often called. It does the same thing. It turns the carbonyl here into an alcohol. It's the same thing as the sodium. It's a similar type of concept as the sodium borohydride. In both cases, boron and aluminum are both in group 3. They both, if they have 4 bonds to this hydrogen, they both have a negative formal charge because they've got 4 dots, right? Same for the aluminum here, the 4 dots, but they're in group 3, so they'd prefer to have 3. So that's negative formal charge. It's 3 minus 4 is negative 1. And so these are ionic compounds where we have basically a polyatomic ion that is a negative ion. These provide that hydride ion. When they get rid of the hydride ion, then they are no longer having a formal charge. And so that makes them good reducing agents. Reducing, why? Because they're giving the hydrogen. So remember, when something gets hydrogen, it's getting reduced. So by giving the hydrogen, they cause the other thing to get reduced. And so they're reducing agents. It's the same exact mechanism with the lithium aluminum hydride. So the hydride ion moves. Notice it's not a proton transfer. The hydride ion is a nucleophile. These electrons here go and make a bond. We have this resonance arrow here showing the electrons here in the oxygen so that this carbon is not making 5 bonds. And then we have to protonate. So we need to have a protic solvent or protic workup here to provide the proton afterwards. But those are the common ways to reduce a carbonyl to an alcohol. They are more common than the catalytic hydrogenation because they require less energy. So one other thing to keep in mind too is that the sodium borohydride and the lithium aluminum hydride are what we refer to as soft reducing agents. They're not going to reduce everything. So the H2 platinum, we already saw before, that's going to reduce the alkenes as well. So you'll lose any double bonds that you have. But if you want to retain the carbon-carbon double bond while reducing the carbonyl, you can use these soft reducing agents, sodium borohydride, lithium aluminum hydride. That's going to be their primary usage in synthesis, okay? You might want to make a note. When you're doing synthesis and you want to reduce the carbonyl to an alcohol, but you don't want to reduce the alkene, you're going to use these soft reducing agents. Sodium borohydride, lithium aluminum hydride. Either one. So also sometimes there are substituents on these. So it doesn't have to be all hydrogens on the aluminum or the boron, just one, the one that you're going to give away. So other groups can be used to kind of tune in. For example, if you have sterically hindered groups, that can make it so that it can't get into certain places in a molecule, and so forth. So there are deviations to these, but the key component is the boron and the aluminum with a hydrogen atom attached here. You can also reduce, with lithium aluminum hydride, you can also reduce carboxylic acids and esters. When you reduce a carboxylic acid, you get an alcohol. And when you reduce ester, you get an alcohol. You also get the side product here. So you get the alcohol from the carbonyl, but you also get this part that kind of comes off and that's what makes the methanol. We'll talk more about these reactions when we get to reactions of carboxylic acids and esters in Chem 213. But here's the mechanism anyway. So these are going to become more important reactions later, but the mechanism is like this. You've got the lithium aluminum hydride, same first step, nucleophilic attack by the hydride ion, and then a resonance arrow here to put a negative formal charge on the oxygen. But at this point, we have the loss of the leaving group, which is going to be methoxide ion. At that point, we've just got an aldehyde, and so the rest of the mechanism is the same as we saw before. We have the attack by the hydride again. The alkoxide ion gets protonated, proton transfer, and then we get the product here. So no big surprises here. The big unique step is this one right here, where we lose the methoxide ion, right? That said, methoxide is not a great leaving group, but the intermediate here is very high in energy, so it kicks this off because the aldehyde is much lower in energy. So we know that these anions with oxygen, like hydroxide, methoxide, ethoxide, are generally terrible leaving groups, but in this case it will leave because you get this stable intermediate product, the aldehyde. And that's going to be it for this lecture. That'll be the end of this lecture. As we move forward, we're going to talk about more reactions of alcohols, and I'll see you in the next one.